Hi and Assalamualaikum to IRTI SHAMRUL-MAR bin SHAMSUDDIN. My name is Nurul Afika binti Sharizan. My number matric is DF210072. Today I will briefly share 2 key points and introduction to our company, Buildwise Engineering Consultant, and our project. Buildwise Engineering Consultant is a leading Malaysian firm with over 25 years of experience and more than 50 successful projects. The company specializes in civil, structural, geotechnical and environmental engineering, serving both public and private sector. So for the service offer, we provide project management and construction oversight, detailed engineering design and specialized solution for highway and road design, drainage and irrigation system. So for the mission and vision, our mission is to deliver top quality engineering services that exceed client expectation and support sustainable infrastructure growth. Meanwhile, our vision is to be the go-to consultancy known for innovation, great service and sustainable results. One of our recent projects is a 5-story apartment in USJ 25 Subang Jaya, valued at RM55 million with a timeline of 18 months. It involved structural and infrastructure design for foundation, beam, column and slab, showcasing Buildwise expertise in sustainable and innovative solution. And the table given is the further detail about the project. This is the organisation chart for our company, which include Chief Executive Officer, Structural Engineer, Infrastructure Engineer and also Geotechnical Engineer. Next, this is the structural design schedule that we refer in our project for the design and calculation process.
Assalamualaikum and hi, my name is Aisha Fariha binti Kamar Zaman with metric number is DF210037. I will presenting the overview of the beam design focusing on both specification and detailing. In our project, the beams are designed with dimensions of 150 multiple with 450 mm covering spans of 2400 mm. The materials used include concrete with a characteristic strength of 30 MPa and steel with a strength of 460 MPa. To protect the reinforcement, a concrete cover of 25 to 35 mm is applied. After calculating continuous and simply supported beam, this is the detailing that we get at a specific location. Detailing show that the reinforcement bars are placed to handle bending moments effectively with the top and bottom reinforcement position for both continuous and simply supported beams. Stirrups are added at precise intervals to resist shear forces, and the design also accounts for all loads including dead loads like the beam self-weight and live loads, and ensuring safety and structural stability. Overall, this design combines efficiency, durability, and compliance with engineering standards.
For slab manual calculation, in this project we apply the design of two-way resistance slab. Firstly, we have to obtain the parameter that will be used for the calculation, which is LX 3050 mm, LY 5800 mm, characteristic action, permanent GK and variable QK, design of life for 50 years, R60 fire resistant, exposure class of XC3, FCK 30 Nm², FYK 460 Nm/mm², unit weight of concrete 25 kN per meter cube, then the diameter bar assumed as 10 mm. For this project, the slab 5B to 6/AC was designed for the slab part. Determination of one-way or two-way slab was through the division of Ly per Lx. If the value is less than 2, it is considered as two-way slab. Then the calculation is proceed with slab thickness, which the H is 135 mm. From the design of durability, fire and burn requirement, the value of C0, which is C min plus C def, is 35 mm, and 30 mm C0 will be used in this design. Then the calculation proceed with design action, which the value is 8.84 kN per meter cube. For the analysis part, the slab is considered as case 2, one shot H discontinuous based on table 3.14 BS Act 110. Based on the main reinforcement analysis, the secondary bar used for the slab is size of H10 300 AS provided is 262 mm3 per meter, higher than calculated. Meanwhile, main bar for short and long span size of H10 300 is used for bottom and top, which is 262 mm3 per meter as provided. Then proceed with analysis shear. The value of VRDC is less than VED in this analysis, which is okay. For deflection analysis, L per D for actual is less than L per D allowable, which is also okay for this project. For cracking checking, the H value is less than 200 mm, and the checking also applied for the main bar and the secondary bar, which both pass the checking, indicating that it less than spacing maximum of slab. Further is the detailing drawing for the slab.
Hi and Assalamualaikum. My name is Norshan binti Norsha and my metric number is DF21011. So today I would like to talk about our column calculation and analysis for this section, which is F 4D, and the position is side. So the specification for our size column is 400 x 400 mm. So the main beam axis is Z and the second beam axis is Y. So the main beam and secondary beam size is 150 x 450 mm. So the design load for Z-axis have two value, which is 19.18 kN per meter. Meanwhile, for the second one is 18.15 kN per meter. So for the axis Y, the value is 16.27 kilonewton per meter for the design load. So next is our action on beam. So the distribution of load from slab to beam for span EF of 4B to 4D, the design load is 7.79 kilonewton per meter. Meanwhile, for the span EF at 4D to 5A, the design load is 8.48 kilonewton per meter. So the total load is 16.27 kilonewton per meter. So for the axial force, it has two separate part, which is the ground floor to roof, which is the value is 74.69 kilonewton, and the second one is footing to ground floor, and the value is 66.32 kilonewton. So for the bending moment, at the moment in column, at the top is 0.30 kilonewton meter, and the fixed end moment is 0.5 kilonewton per meter. So moment in upper column at each level is 0.19 kilonewton per meter, and the moment in lower column is 0.19 kilonewton meter also, and the fixed end moment is 0.5 kilonewton per meter for each level also. So at the last one, for the moment in lower column, the value is 0.25 kilonewton meter. So for axis Y, the moment in column at the top one is 5.83 kilonewton per meter, and the fixed end moment is 7.81 kilonewton meter. So moment in upper column for each level is 3.34 kilonewton meter. Meanwhile, for the moment in lower column is 3.34 kilonewton meter, and the fixed end moment is 7.81 kilonewton meter for each level also. So moment in lower column for the last one is 4.71 kilonewton meter. So determination of non-slender or slender column, we need to consider the column for our ground floor to first floor is slender or non-slender. So after all the calculation, we got both axis is non-slender because of the value is 240.1 is greater than the slender ratio, which is 16.77 for the z-axis, and the y-axis is 40.10. Is our design moment, design of non-slender column bend about both axes. We need to check the biaxial bending. So our calculation is need to ignore the biaxial bending because we have lower value from the stated. Our reinforcement design, which is our AS minimum for this first is 19 mm square or 320 mm square, and for the AS max is 6400 mm square, and we use 4H and 12 for the bars, and the provided is 452 mm square. So for the length of diameter minimum is 3 mm or 6 mm, and the SB max is lesser than 240 or 300 or 400, and we use H6 and the provided is 225. So at the section 400 mm below and above beam and at lap joint, the SB max is 144 mm, and we use H6 and the provided is 125 value. So after checking the biaxial bending at the steel area for the all location and at axis Z and axis Y, we use 4H and 12 as the bars, and the AS provided is 452 mm square. The value for our biaxial bending is 0.05, which is lesser than 1.0, so it is determined as okay.
Assalamualaikum, my name is Nur Husnina binti Nisa. My matrix number DF210070, and I will explain how to design a pie cap manually based on the Eurocode 2. First, the size of the pie cap was determined as 600 times 500 with thickness of 1000 mm. This size satisfied the maximum service load per pie, ensuring the stability and the strength. Next, we perform the analysis. For the main reinforcement, the calculated longitudinal reinforcement area was 176 mm square, and we provide an approved area of 1151 square millimeter using 10 bars of H12. For transfer reinforcement, the calculated area was 42 mm square, and we provide an approved area of 2850 mm square using 14 bars of H60. Shear checks were conducted and passed for vertical shear, punching shear and maximum punching shear, ensuring the pie cap can resist all applied forces effectively. For cracking control, we verify bar spacing. The maximum calculated spacing were 58 mm and 110 mm, both of which are within the allowable limit of 275 mm as per Eurocode 2. So the pie cap design meets all the structural requirements, including reinforcement, shear and crack control, to ensure the safety and compliance with the code. Next, I will explain the process of designing in STEAM software. First, we start with the project parameters, setting the design code as Eurocode 2 and defining material properties such as concrete strength, steel strength and the unit weight of concrete. Next, during the initial setup, we start a new project, define the project name and location, and set Eurocode 2 as a standard. For structural modeling, we add elements like beams, columns, slabs, brick wall, and foundation based on the architectural layout. Loads are inbuilt, including dead loads from software and live, and imposed loads following Eurocode guidelines. We also define structural grids and levels, including 5 levels with the ground floor. Then we proceed to analysis and design, running a structural analysis to evaluate the behavior of elements under applied loads. Next, the verification and validation phase. We check that all structural elements comply with the design standards, address any warning or error, and generate detailed reports. Finally, we move to detailing and report, producing structural drawing with reinforcement details and exporting them to AutoCAD for further review.
Next, I will discuss about structural output generated using STEAM software for our analysis. So this is our graphical output, which provides multiple views including 3D, front, side, top and bottom perspective. These visualizations help engineers access the overall structural integrity and load distribution. Then, we move to the design checks. This ensures that all structural components such as beams, columns, and slabs comply with safety standards and design codes with clear pass or fail results. The software also performs load calculations, analyzing the live, wind, and seismic loads to understand how forces interact within the structure. Another crucial output is the analysis results, which covers stress distribution, deflection, and internal forces like bending moments and shear forces. This helps in evaluating how the structure responds to applied loads. Additionally, we have material and section properties, which provide data on material strength, elasticity, and dimensions to ensuring structural adequacy. The deflection and stability analysis determines whether deformations remain within permissible limits and ensuring safety against buckling or excessive movement. Finally, STEAM generates construction and fabrication details, including reinforcement layouts and connection specification, aiding contractor during execution. Therefore, the STEAM output is essential for validating structural performance, optimizing design, and ensuring safety.
So next is our comparison manual calculation and STEAM. This one is about slab. So on our manual calculation, the specific uniform reinforcement of H10 to 300 for both the top and bottom layer, prioritizing safety through a conservative approach. This result is higher material usage without fully considering the actual load distribution. So meanwhile, for the STEAM software, the optimized reinforcement, it is optimized the reinforcement to H10 to 250 for the bottom layer, and for H10 bars and 225 mm is for the top layer. So it is reflecting the actual bending moment and load requirements. So this efficient design reduces the material usage without compromising the safety. So STEAM's ability to refine design based on the load distribution resulted in a cost-effective and efficient slab design compared to the blanket approach of manual calculation. The beams, we have simply supported and continuous beam. So at simply supported beam in grid D1 at 2B to 2D, the manual calculation recommended that we use 2H and 10 bars with a provided reinforcement area of 157 mm square, which is exceeding the required area, which is 117 mm square. So for the STEAM suggests that we use 2H 12 bars, providing a more precise reinforcement area of 226 mm square, just above the required area, which is 207 mm square. So for continuous beam in grid F for 4B to 5B, for the manual calculation recommended 6H for 6 bars with a provided area of 1.70 mm square, far exceeding the required 65 mm square. Meanwhile, for the STEAM calculation, it optimized it to 2H and 12 bars, aligning the required area, which is 1.59 mm square, with a provided area of 226 mm square. So STEAM accounted for load redistribution and continuity effects, delivering a balanced design that avoided unnecessary material use since in the manual approach.
Next, I will present the comparison between manual calculation and esteem software for the column design at grade 6C middle. Using the manual approach, we propose 2 #10 bars with a provided reinforcement area of 457 mm², which significantly exceed the required 49 mm². In contrast, esteem designed a combination of 4 #20 and 8 #12 bars providing 1257 mm² and 905 mm² of reinforcement respectively. This design closely matched the actual axial load and moment demands of the column. Next, I'll compare the foundation design for piles at grade F4 using manual calculation and esteem software. In manual calculations, we suggested using 10 #12 bars providing 1131 mm² of reinforcement for a required 921 mm. On the other hand, esteem software recommend a stronger design with 14 #16 bars providing 2850 mm² of reinforcement for a required 2273 mm². The software also included other options like 6 #12 or 3 #12 bars to handle different load scenario. The main advantage of esteem is that it uses advanced calculations taking into account things like soil and load changes, resulting in a safer or more flexible design.
To conclude what we have gained from the Integrated Design Project course, the first one is real-world insight. We experienced how site condition, regulation and client requirements shape real-world project. This was invaluable in bridging theory with practice. And the second one is project management. We learned to plan, schedule and manage resources effectively, balancing time, budget and quality constraint. And the third one is team collaboration. Working in a multidisciplinary team taught us to communicate and coordinate effectively, ensuring all contributions align with the project goals. And the last one is critical thinking and innovation. We develop problem-solving skills by tackling challenges creatively and proposing sustainable solutions. In summary, the IDP course provides us with practical knowledge, management, expertise, teamwork skill and innovative thinking, preparing us for future engineering challenges. Thank you.